This is a short introduction about cable cars. So, a cable car in the context of mass transit is a system using rail cars that are hauled by a continuously moving cable running at a constant speed. Individual cars stop and start by releasing and gripping this cable as required. So we will have 5 main components to start the cable. So the cable, the grip, the powerhouse, the cars, the brakes. So how cable car works? Cable cars have no engine or motor on the cars themselves. The power source is centralized in the cable car barn and powerhouse. There are powerful electric motors that drive giant winding wheels that pull cables. Each cable has its own set of winding wheels. The rearmost winding wheel in each is adjustable. When a cable is new, this rearmost wheel is close to the other winding wheels. As the cable naturally stretches out with the use, the wheel is gradually moved back by shop workers to keep constant tension on the cable. The cables are over an inch in diameter with 6 steel strands of 19 wires each wrapped around a core of sisal work. Each cable has a mechanical grip that latches onto the cable, much like a huge pair of pliers. The gripman can take or drop the rope as needed to start or stop the car. The cables move at a constant 9.5 miles per hour. If a cable car is going faster than that, it is a sure thing that the car is going downhill. The grip is not holding the rope tight.
Hi, I'm Mark Luis M. Lubrin, an AC student from the class of MEC32 B11 under Engineer Pilones, and I'm going to discuss our objectives in making the miniature model of the cable car and the materials in making it. So, our first objective is to be able to apply the principle of mechanics, especially about the strength of materials within our project. Next is to make a project that is within the scope of our program, which was about electronics. With these objectives, we made a model of a cable car which can be controlled using a remote control. It can easily be done with the use of these materials. First is a popsicle sticks, which will serve as a foundation of the tower. Next is a barbecue stick for the roof of the cottage, a wood glue to stick each materials into place, a yarn and a nylon string for the guide of the cable car, and a DC motor and a circuit diagram of an infrared detector for the electronic part of the project. So, again, I'm Mark Luis M. Lubrin. Thank you.
Hello, I'm Christian Orcino, and I'm here to present to you how to get the tension required to pull our cable car and the torque of our DC motor. For better understanding, I will present to you an illustration of our cable. So here is our illustration of our cable car. We have measured a distance of 46 cm here and the height of 39 cm here. Getting the arctangent of 39 over 46, we could get the angle here of 40.30 degrees. We also have a known mass of the cable car, which is 177 grams. So we multiply it by 9.8 to get the weight, which is equal to 1.73 newtons. Then the next thing that we will do is to get the tension. This is the tension. From this free body diagram, we could get an equation of T minus W sine theta is equal to 0. Therefore, we can say that the tension is equal to the W sine theta. From our values before, we can substitute the W and the theta. So, therefore, the tension is equal to 1.73 sine 40.30, which is equal to 1.1189 newtons. So, this is the tension required to pull the cable car. For the torque, we just multiply this force by the distance from the shaft. The radius of the shaft of our DC motor, which is 1 centimeter. Therefore, we could say that the torque is equal to this value multiplied by 1 centimeter, and therefore we could get a value of 1.1189 Newton centimeter. There you have.
Hi, I am Lorenz Caballero, and I'm about to discuss to you the stress, the strain, and the maximum weight that the cotton yarn string of our cable car model can sustain. So let's start things up. The first value that we are going to compute is the stress of the cotton yarn string. So as you have known, stress is equal to force over area. So it's pretty straightforward. The force that we are going to use is the force that is computed a while ago by my groupmate Christian Orcino, and this value, the tension, is equal to 1.1189 newtons. And as we have searched in the net, the average cross-sectional area of cotton yarn string is 0.65 millimeters squared. So substituting the values, we can get we will get the formula: stress is equal to 1.1189 newtons over 0.65 millimeters squared. So calculating it, the resulting stress is 1.72 megapascals. So that stress is relatively small, and we can say that the cotton yarn string does not experience much stress. Next thing that we are going to compute is the strain of the cotton yarn string. So as we have learned, the elongation or the strain of a cotton yarn string is equal to the force times the length of the string over its cross-sectional area times the Young's modulus. The Young's modulus that we are going to use, we have searched it from the net, and the value that we have come up with is equal to 8 gigapascals, so which can be translated to 8,000 megapascals, and the length of the nylon string that we have used is equal to 603 millimeters. So again, it's pretty much straightforward. Substituting the values, we can get the formula for strain as 1.1189 newtons times 603 millimeters over 0.65 millimeters squared times 8,000 megapascals. Plugging it into the calculator, solving it, and we will get an elongation of 0.13 millimeters. The 8,000 gigapascal Young's modulus of the cotton yarn string is its maximum value, meaning the elongation that we have computed is the minimum elongation. Therefore, the elongation can be greater than our computed value, which is 0.13 millimeters, depending on the string that is used. And next, the last thing that we are gonna compute is the maximum weight that the yarn string of our cable car model can hold. So with some analysis, we know that the stress is equal to the force tension over the area. So manipulating it, we will get that the stress times area is equal to the tension, and we will use the stress as the maximum as 8 gigapascals, and pretty much straightforward. The tension that we will get is equal to 8,000 megapascals times 0.65 millimeters squared, and we will get tension of 5.2 newtons. A while ago, we will recall that the tension is equivalent to weight sine theta, and computing for the weight is equal to tension over sine theta. Substituting values, we will get weight is equal to 5.2 newtons over sine 40.3 degrees, and we will get the weight as 8.04 newtons. And weight, as we know, is mass times the gravitational acceleration g. So to get the mass, we should divide the weight by g. So 8.04 newtons divided by 9.8 meters per second squared, and the maximum, we will get that the maximum value of the mass that our cable car model can support is approximately 820 grams. So that's all, and thanks for watching this video. Have a nice day.